Work, power and energy. Work. What is work, or when work is said to be done? When the point of application of force moves in the direction of the applied force under its effect, work is said to be done. Mathematical definition of work. Work is defined as the product of force and displacement in the direction of force. This is the object and we are applying force on the object, and by applying the force, object moves to the distance or displacement, yes, displacement. Then W equal to F into S. If force and displacement are not parallel to each other, rather they are inclined at an angle, theta angle, like this, then in the evaluation of work component of force in the direction of displacement will be considered as F cos theta into S. Work, power and energy. Work. What is work, or when work is said to be done? When the point of application of force moves in the direction of the applied force under its effect, work is said to be done. Mathematical definition of work. Work is defined as the product of force and displacement in the direction of force. This is the object and we are applying force on the object, and by applying the force, object moves to the distance or displacement, yes, displacement. Then W equal to F into S. If force and displacement are not parallel to each other, rather they are inclined at an angle, theta angle, like this, then in the evaluation of work component of force in the direction of displacement will be considered as F cos theta into S. That is, W work done W equal to F cos theta into S is nothing but F S cos theta. Therefore, work done W equal to F S cos theta. Here theta is the angle between the direction of the force and the direction of displacement. Vector definition of work. Force and displacement both are vector quantities, but their product, work, is a scalar quantity. Hence, work must be scalar product or dot product of force and displacement vector. That is, W equal to F dot S. Work done by variable force. Force varying with displacement. In this condition, we consider the force to be constant for any elementary displacement, and work in that elementary displacement is evaluated or calculated. Total work is obtained by integrating the elementary work from initial to final limits. That is, dW equal to vector F dot vector ds. That is, W equal to, that is, the integral of dW is W equal to integral S1 to S2 F dot ds. Force varying with time. In this condition, we consider the force to be constant for any elementary displacement, and work done in that elementary displacement is evaluated or calculated. dW equal to vector F dot vector ds. Multiply and divide by dt in this equation. dW equal to F dot ds by dt into dt. We know ds by dt, that is the rate of change of displacement, is velocity. Therefore, dW equal to F dot v into dt. Now, total work is obtained by integrating the elementary work from initial to final limits. W equal to integral T1 to T2 F vector dot v vector into dt. F dot v into dt. Work done by variable force from graph. Let force be the function of displacement and its graph has been shown. That is, force taken along y-axis and displacement S taken along x-axis. Then curve obtained as AB. At A, displacement is S1 and at B, displacement is S2. Then dW equal to F dot ds. dW equal to length into breadth of strip mn into ds. That is the area of strip mn ds. Thus, work done in any part of the graph is equal to area under that part. Hence, total work done from S1 to S2 will be given by the area enclosed under the graph from S1 to S2. W equal to area A, B, S2, S1 into A. So the area under the curve A, B, S2, S1, A, that only work done for this curve A, B. Different cases of work done by constant force. Case 1. Force and displacement if acting same direction. Then theta, that is the angle between the direction of force and displacement, is 0. Then W equal to Fs cos theta becomes W equal to Fs cos 0. As we know, cos 0 is 1, W equal to Fs. Example, coolie pushing a load horizontally. This is an example for force and displacement acting in same direction. Second case, force and displacement are mutually acting perpendicular to each other. For this theta, angle between force and displacement theta equal to 90 degree. And W equal to Fs cos theta, that is Fs cos 90. Cos 90 we know 0, therefore W equal to 0. Example, coolie carrying a load on his head and moving horizontally with constant velocity. Then he applies force vertically to balance weight of body and its displacement is horizontal. Third case, force and displacement are acting in opposite direction. In this case, theta equal to 180 degree. Therefore, W equal to Fs cos theta becomes Fs cos 180 degree. We know cos 180 is minus 1. Therefore, W equal to minus F into S. Example, coolie carrying a load on his head and moving vertically down with constant velocity. Then he applies a force in vertically upward direction to balance the weight of a body and its displacement is in vertically downward direction. Energy. What is energy? Energy is a capacity of doing work by a body. That is energy. Energy possessed by the body by virtue of any case is equal to the total work done by the body when the cause responsible for energy becomes completely extinct. Some types of energies. There are different types of energy. They are mechanical energy, electrical energy, magnetic energy, nuclear energy, solar energy, chemical energy, etc. Let's discuss mechanical energy. Mechanical energy is the energy possessed by the body by virtue of which it performs some mechanical work is known as mechanical energy. It is basically two types. First one, kinetic energy. Second one, potential energy. Kinetic energy. Kinetic energy is the energy possessed by a body due to virtue of its motion, that is kinetic energy. Kinetic energy possessed by moving body is equal to total work done by the body just before coming out to rest. Consider a man moving with velocity v naught. After traveling through distance s, it comes to rest. Then u equal to v naught and v final velocity becomes 0 and s is a displacement. Applying this in third equation of motion, that is v square equal to u square plus 2as. As final velocity v equal to 0 and initial velocity is v naught, then 0 equal to v naught square plus 2as. From that 2as equal to minus v naught square. From this we can simplify a equal to minus v naught square by 2s. Hence force acting on the body F equal to m into a. And just now only we derived a as a equal to minus v naught square by 2s. Substituting this here, F on the body is equal to mv naught square by 2s. But from Newton's third law of motion, that is every action equal and opposite reaction, from that force applied by body is equal to opposite and to the force applied on body. That is force applied by body is equal and opposite to the force applied on body. This is the Newton's third law of motion. Here negative sign indicates that it is in opposite direction. And just now only we derived F equal to mv naught square by 2s. Just substituting that, minus minus getting cancelled, then mv naught square by 2s. Therefore, work done by body W equal to F dot S and W equal to mv naught square by 2s into s by cos 0. S getting cancelled and cos 0 is 1. Therefore, W equal to half m into V naught square. Thus, kinetic energy stored in the body is kinetic energy equal to half mv square. Next, kinetic energy in terms of momentum. Kinetic energy of body moving with velocity v is kinetic energy equal to half mv naught square, and multiplying dividing by m, k equal to half mv square into m by m. And if you bring this m inside, half into m square v square by 2m, we know momentum P equal to m into v. Substituting this here, k equal to p square by 2m. K equal to p square by 2m is the relationship between kinetic energy and momentum. Potential energy is the energy possessed by the body by virtue of its position or state of rest is known as potential energy. Example: gravitational potential energy, elastic potential energy, electrostatic potential energy, etc. Gravitational potential energy is the energy possessed by a body by virtue of its object above surface of earth is known as gravitational potential energy. It is equal to the work done by the body situated at some height in returning back slowly to the surface of earth. Consider a body of mass m situated at height h above the surface of earth. Force applied by the body in vertical downward direction is F equal to m into g. Here g is the acceleration due to gravity. Displacement of the body in coming back slowly to the surface of earth is S equal to h. Hence, work done by the body W equal to Fs cos theta, and theta, that is both force and displacement acting in the same direction. Therefore, theta equal to 0. We know cos 0 is 1. Therefore, W equal to Fs cos 0 becomes W equal to Fs, and F equal to m into g, and S equal to h. Then this work was stored in the body in the form of gravitational potential energy due to its position. Therefore, gravitational potential energy equal to m into g into h. Elastic potential energy is the energy possessed by spring by virtue of compression or expansion against elastic force in the spring is known as elastic potential energy. Spring is a coiled structure made up of elastic material and is capable of applying restoring force and restoring torque when disturbed from its original state. When force is applied at one end of the string parallel to the length, then keeping the other end fixed, then the spring expands or contracts and develops, and restoring force F naught, which balances the applied force in equilibrium. On increasing applied force, spring further expands in order to increase restoring force for balancing the applied force. Thus, restoring force developed within the spring is directed proportional to the extension produced in the spring. dW equal to minus kx into dx. Total work done by the spring in regaining its original length is obtained as integrating dW from x0 to 0. Then W equal to integral in x0 to 0 minus kx into dx. And if you integrate this x value, you will get x squared by 2 by substituting upper and lower limit. Then W equal to minus k into 0 square by 2 minus x naught square by 2, and W equal to minus k into 0 minus x naught square by 2. This work was stored in the body in the form of elastic potential energy. Elastic potential energy equal to half into k x naught square. Work energy theorem. It states that total work done on the body is equal to change in kinetic energy provided body is confined to move horizontally and no dissipating forces are operating. Consider a body of man m moving with velocity, initial velocity v1. After traveling through displacement s, its final velocity becomes v2 under the effect of force F. Now initial velocity u equal to final velocity v1 and v equal to v2, s equal to s. applying third equation of motion, that is v square equal to u square plus 2as. Then if you have two cases, then v2 square equal to v1 square plus 2as. A equal to v2 square minus v1 square by 2s. Hence, external force acting on the body is F equal to m into A. By substituting F equal to m into v2 square minus v1 square by 2s. Therefore, work done on body by external force W equal to F vector dot S vector, and F equal to, we derived m into v2 square minus v1 square by 2s into S. S is resolved to two component and horizontal component will be taken or considered, that is into S cos theta. As force and displacement are in same direction, cos theta, that is theta equal to 0. Cos 0 is 1. Then W equal to half m into v2 square minus half m into v1 square. Half m v2 square is called k2 and half m v1 square is k1, and W equal to delta k. W equal to delta k. That is, work done on the body is equal to change in kinetic energy. Principle of conservation of energy or law of conservation of energy. Law of conservation of energy states that energy can neither be created nor be destroyed, but it can only be converted from one form of energy to another form. Consider a body of man m situated at height h and moving with velocity v0 or v0. Its energy will be E1 equal to P1 plus K1. E1 is the total energy, P1 is the potential energy, and K1 is the kinetic energy. Potential energy is equal to mgh joules formula we know, and kinetic energy equal to half m v0 square. The body falls under gravity through the distance y, then it acquires velocity v1 and its height becomes h2 y, and initial velocity u equal to v0 and displacement s equal to y. Acceleration is equal to acceleration due to gravity g, and v equal to v1. Substituting this in equation of motion, third equation of motion, v1 square equal to v0 square plus 2gy.